Hi. So in the next two lectures on wave packets and the uncertainty principle, the goal is that, so if you don't already, you'll understand this XKCD cartoon, which is excellent. By the way, if you're not a fan of XKCD, I highly recommend you checking it out. It's really super funny. Now, before we get into talking about quantum waves and wave packets and all that great stuff, it's probably a good idea if we review a little bit the terminology and the math of classical waves. So let's go over some classical wave motion. Now, de Broglie matter waves, we usually use the symbol psi to indicate. And if you have a single wave, a free wave, then we could define that as a sine or a cosine function like here. So our position is x. We're going to just assume that it's propagating in one dimension, and it's moving in time, t. And a is the amplitude of our wave, lambda is the wavelength of our wave, and v is the speed of the phase of this wave. So this is a solution of the classical wave equation, by the way, in addition to the Schrodinger equation. And remember that the classical wave equation is the partial derivative, the second partial derivative of the wave function with respect to the spatial coordinate is equal to 1 over v squared times the second derivative, partial derivative of the wave function with respect to the time coordinate. Now we're going to define our wave number k and our angular frequency omega like this. K is equal to 2 pi over lambda and omega is equal to 2 pi over the period t. Now you have to do this because the arguments of your sine and your cosine functions have to be dimensionless. In other words, they have to be in radians. So now if we write it that way, then our wave function psi of xt could be written as a times sine kx minus omega t. So that's one way to write a wave. Okay, so that's a review of the notation and what everything means. Now the phase velocity is the velocity of a point on the wave that has a given phase, for example the crest. Okay, so if we wanted to track the speed of the crest of that wave as it moves in time, then that would be equal to lambda the wavelength divided by the period t. Now, given our definitions of omega and k, that also means that the phase velocity can be written as omega over k, the wave number. Now, if we have a phase constant, here symboled phi, then that's going to shift the wave to the right or the left. Okay, so if you want to do that, then you add it into your sine argument, so you have a sine kx minus omega t plus phi. So that's just kind of a general classical wave definition. Now to review these concepts, let's do a little example problem. Let's consider that you have a simple sinusoidal ocean wave with an amplitude of 1 meter, a wavelength of 5 meters, and a speed of 5 meters per second. Now since we know that v is equal to lambda f, v is equal to the wavelength times the frequency, which is the wavelength over the period, then we know that the period is 1 second, just solving. Because our speed is 5 meters per second and our wavelength is 5, so we know that the period is then 1 second. So that gives us the following wave function. Psi of x and t, the function of the wave function with respect to the position of the time, is equal to 1 meter times the sine of 2 pi times x over 5 meters minus t over 1 second. Now, if you want to look at how that evolves in time, let's plot snapshots of that wave at different values for our time coordinate t. So I did this in Maple. And here you have your wave function. I wrote it out as a function of time and space. And then what I'm going to do is just plot as a function of the spatial coordinate, but plugging in for different values of the time. So if I substitute in t is equal to 0, that's going to be colored in red. And if I substitute in t is equal to 1/4 of a second, then that'll be colored in blue. T is equal to 1/2 a second, that's green, and then t is equal to 3/4 of a second, that's in yellow. And so you can see that as you move through in time, it moves that wave to the right, which is what happens when you subtract off your minus omega t there. Okay, so that's a review of some notation for classical waves and just standard sort of sinusoidal waves. Now let's get a little bit more into what we mean in quantum mechanics with the quantum particle. So remember that we define the quantum particle as a new model that's a recognition of the dual wave-particle sort of wave-particle duality of everything. Basically, light, photons are both waves and particles, and also matter, such as electrons, for example, can act simultaneously as a wave and a particle. They have both wave and particle characteristics, and which model you use to describe the entity in question is just whatever phenomena you're trying to describe. So, for example, if something is diffracting, then you're going to use the wave nature to describe that. Whereas, if you have a photon interacting with a material, when it interacts with another material, usually the particle model is best for that. Now, an ideal particle has zero size, so it's very localized in space. But an ideal wave is a single frequency and it's infinitely long. Our sinusoidal wave from before is a good example. Therefore, it's unlocalized in space. But what we can do is build localized entities using Fourier series, using Fourier mathematics. Okay? So we use infinitely long waves and we sum up a bunch of those, and that helps build little localized entities. So real waves, real wave packets, are always localized in space. And we call waves that are localized in space wave packets. And a little cartoon of a wave packet is pictured here. Now, how do you get a packet? Well, you have to sum up waves. You have to superimpose them. And then what happens is the waves add constructively at the location of the particle or the packet, and then there's destructive interference pretty much everywhere else. And that gives you your wave packet. And that's kind of shown here. It's showing you that you have the constructive interference here in the center where there's this envelope with a packet inside, and then outside of that you get the destructive interference. Now the mathematics behind all this, the mathematical description of summing many waves to form a wave packet, is using Fourier mathematics or Fourier series. Now Fourier series can be summed up mathematically here. This is just for the spatial coordinate. Psi of x is equal to a naught over 2 plus the infinite sum, n equals 1 to infinity, of a coefficient a sub n times the cosine of n pi x over L plus b sub n times sine of n pi x over L. Now our restrictions here are that our wave function be piecewise continuous, and the function has to be defined over a period of 2L. So what that means is that either the function repeats after a period of 2L, or you're only interested in that 2L range either way. So this would normally mean that our total wavelength for the function is 2L. Now normally we define a wave function like cosine of kx minus omega t. And here you can see that k is our wave number, and that's equal to n pi over L here in this Fourier series, right? Cosine of kx, and here k is n pi over L. So what that means is that our wave numbers are varied in that sum automatically. Now for simplicity, we're just ignoring the time term for now. However, you can imagine that the mathematics could be extended to include a time term with relative ease. Now, just imagine what we're going to do, since we're ignoring the time term, is that we're just taking a snapshot of our wave function or our wave packet at a particular instant in time. Okay? Now I'd like to do a Fourier series example to kind of remind those of you that might have seen it before and maybe introduce the concept to those of you that this is a new idea. So basically, if you remember our definition of that Fourier series, actually let me flip back to it real quick. Here you have this a naught over 2 term. That's just a constant offset if you want to lift your wave function up above 0 for whatever reason. Okay, so that's your constant offset. And then here, these are the varying terms with an and bn. So those are going to be the amplitudes of the cosine and the sine terms. Now by varying those amplitudes an and bn and summing over enough terms, you can get almost any shape that you might be interested in. So, for example, let's look at a square wave, because that's one of the simplest things to look at. The wave function here is defined as psi of x is equal to plus 1 for a range of x equal to 0 to pi, and then 2 pi to 3 pi, and so on and so forth. It repeats. The wave function is equal to minus 1 for pi to 2 pi, 3 pi to 4 pi, and so on and so forth. And that's pictured here, okay? Now the Fourier series, which describes this function, is described this way. Psi of x is equal to 4 over pi times sine of x plus sine of 3x over 3 plus sine of 5x over 5 plus sine of 7x over 7, and then it keeps going. It's an infinite series. Now, if I just take the first 8 terms in that infinite sum and then sum them all up and plot that out for you, here I did it in a program called Maple, then you can see that it's already starting to look like a square wave function, okay? There's some squiggles in the top and the bottom of my square wave, but the more terms I add into my infinite sum, the more those will get smoothed out. Also, the more terms I add into my infinite sum, the more this slope here in between the waves will go from a slanted value to almost straight up and down. And so that's an example. Now, if you know what your function is, you can find the coefficients an and bn. Here I presented what that Fourier series was for a square wave without really explaining it. But you can find those coefficients and figure out what your Fourier series would be with pretty simple mathematics. So the formula to help solve for those coefficients an and bn in the Fourier series looks like this. An is equal to 1 over L times the integral over 1 full wavelength times psi of x times the cosine of n pi x over L dx. So that gives you your an coefficient. Your bn coefficient is 1 over L integrated over 1 full wavelength, psi of x times sine of n pi x over L dx. Okay, so there it is. So now I'm going to prove to you that those coefficients an and bn are what I said they were when I showed you what the square wave was. So let's find those square wave Fourier series from first principles. So remember, my wave function is either +1 or -1, depending upon where you're integrating. So it's piecewise continuous. It's +1, for example, from 0 to pi, and it's -1 from pi to 2 pi. So remembering our formula for our coefficients an and bn presented here, I'm going to plug into those formula and then solve those integrals to find my coefficient. I'll start with an. Now here, realize that 1 full wavelength there goes over a range of 0 to 2 pi. So that means that 2L is 2 pi, or L is equal to pi. So I'm going to plug in for that in my formulae. So a sub n is equal to 1 over pi times the integral from 0 to pi of my wave function +1, now times cosine of n pi x over L, where I've plugged in for L is equal to pi. So I have n pi x over pi dx. Now it's piecewise continuous. I have to integrate over the full 0 to 2 pi range. So piecewise from 0 to pi it was +1, from pi to 2 pi it's -1. So I have +1 over pi, pi to 2 pi times -1 cosine of n pi x over pi dx. Okay, so I'm going to perform those integrals. They're pretty easy to do. All you have to do is integrate your cosine. And when you integrate your cosine, it's going to be the cosine of nx that you're integrating, so you get 1 over n sine of nx. Okay, so plugging that in, I get 1 over pi, 1 over n sine of nx, evaluated from 0 to pi. And now here, remember that my wave function was a -1, so I'm subtracting the second term, minus 1 over n sine of nx, evaluated from pi to 2 pi. All right? Now, this is equal to 0. And it's equal to 0 because the sine of 0 is 0, the sine of pi is 0, the sine of 2 pi is 0, the sine of 3 pi is 0, and you can keep going. So all those terms are 0, which makes my coefficient a sub n, my amplitude, 0. But I've still got to do my bn. Now bn is equal to 1 over pi, integral from 0 to pi times my wave function +1, times the sine of n pi x over pi, which just gives me sine nx, and then dx. And now, piecewise continuous, remember I got to do the second piece. 1 over pi, integrated from pi to 2 pi minus 1, sine of n pi x over pi dx. So I'm going to perform that integral, and when I integrate a sine, I get a minus cosine. So here b sub n is equal to 1 over pi times minus 1 over n, cosine of nx, evaluated from 0 to pi, plus 1 over n cosine of nx, evaluated from pi to 2 pi. Now it's a plus because when I integrate a sine I get a negative cosine, and I'm already subtracting it, so I already had a -1 there, so that changes that value to plus. Now if I evaluate, I'm going to pull my n out, so I get 1 over n pi times minus cosine n pi plus cosine 0 plus cosine 2n pi minus cosine n pi. Combining terms and remembering that cosine of 0 is 1 and cosine of 2 pi, 4 pi, 6 pi, 8 pi, and so on and so forth, that's also 1. So cosine of 0 plus cosine of 2n pi, that's going to give me 2. So here I have 1 over n pi times 2 minus 2 cosine of n pi. Now, This is going to give me 0 if n is an even number. Because remember that cosine of 2 pi, 4 pi, 6 pi, 8 pi, that's always 1. And so then it would be 2 minus 2, and that's 0. It could also be 4 over n pi, and that happens when n is an odd number. And that would be because the cosine of 1 pi, 3 pi, 5 pi, and so on and so forth, that gives me minus 1. And that would mean that I have 2 minus 2, which would give me 4. And then b sub n would be equal to 4 over n pi when it's an odd number. So now I've solved for my two coefficients, okay? So I've got my values of a sub n and b sub n, and a naught because there's no additive offset here. So I know that a naught and a n are 0, and that bn is 0 when n is an even number, and bn is equal to 4 over n pi when n is an odd number. If I plug that in, then that means that my wave function psi of x for a square wave would be equal to 4 over pi times sine of x plus sine of 3x over 3 plus sine of 5x over 5 plus sine of 7x over 7, etc., infinite sum. Okay? So that brings me back to what I showed you already for the sum of terms for a square wave. All right, so I think that's enough to digest for our review of classical waves and our presentation of the beginning of how to form a wave packet mathematically. Now in the next lecture, I'll go over some of the consequences of particle waves and wave packets. See you in class.